A very good evening to Dr. Liu. My name is Shahirah Binti Sabana and I'm going to present my answer to question number 4. So the question that I got, the research question that was made by the student here, it says that more female has a normal BMI compared to male. So you can see that even the research question have a missing terms. So we have to modify the research question. And then the data that was given is the gender of the students, which is the female and male, and then the normal BMI status, which is yes or no. And then the data is unorganized, so we have to organize it in a table and then plot it. So moving on to the modified research question, is UMS female students are more likely to have normal BMI status compared to UMS male students? So the experimental design, the response variables related are the gender and the normal BMI status. Gender is the male and the female student, and the normal BMI status is either yes or no. Experimental unit is the UMS students. The replicates are the 21 UMS students that are involved, and then the sampling is 13 UMS female students and 8 UMS male students. We separated the students according to their gender. Moving on to the data organization. So we organize the data in a table like this. So I included a student ID just to make sure it is more organized. And then the second column is the gender. I start with the female and then continue with the male. And the normal BMI status according to the gender. And then the data that was given in the question. So this is table 1. That shows the summary of data collected to investigate the frequency distribution of UMS female and male students associated with their normal BMI status. So either they have normal BMI status or they do not have normal BMI status. And then this, I also made a second table, table 2, that is easier to observe the difference, whether the female have more or the male have more BMI status, normal BMI status frequency. So this is table 2 that shows the frequency distribution of data sample. As you can see, the total is the same, 21, as the replicates in the experimental design earlier. Moving on to the plot. So I make a mosaic plot for this data, because both variables, which is the gender and the normal BMI status, is not continuous data, it is not numeric, so we cannot make any scatter plot. So the best one is the mosaic plot. So the mosaic plot, this is the title, this is the frequency distribution of UMS female and male students associated with normal BMI status. So in order to make this mosaic plot, we have to go to R. So through R, the first thing that we always have to do is set the work directory. So this is the command to set the work directory. Just type set wd, open the bracket, double apostrophe, and then just copy the file address where you store the data that you make in Excel before. So I made an Excel and then I save it as gender BMI.csv. Make sure to save it as CSV, and then stored in a data in a folder here. This is one, and you just copy the file address here, copy and just paste it in R, and then just add this sign. Make sure that this sign is in pairs. As you can see here, it is, all of them are in pairs, and you just click run. If you click run, you already set the working directory. You can see here it is where I put where I store the data that I already make in Excel before. And then I give the object name, which is gender BMI, and then I just read the CSV to log in the data into R. This is the command to log in the data, and then just include the name of the file before. Don't forget to add the .csv. This is make sure it is the same spelling as the name of the file. Just copy the file name here, gender BMI, just copy them and then just paste it in R. Just click run. If you click run, you can see that the data is already logged in here. As you can see here, this is the same as the one that you make in Excel earlier. Make sure it is the same, even the spelling, so that the R can read it properly without any mistake. And then we have to make a table. We have to construct a table. So I give a table name for this. Table name, just any random name that is related to the data, and then just read as table, open bracket, the object name, dollar sign, the second variable, comma, object name, dollar sign, and the first variable. This is the first variable, this is the second variable. So once I set the table, I give the table a name. I just have to type back the table name, the same as this one. And if you click run, you can see here, the result is here, this one. If you click this is the command, and this is the result. You can see it is the same as the one is in table 2 that I made earlier. Then moving on, to make the plot, you just have to click plot. This is the command to make a mosaic plot, and you just have to type plot, open bracket, the name of the table. So it is very important to make the table before you plot the data. Don't just like directly plot as you always do for the t-test, right? So have to set the table name first and just plot like this so that we can make a mosaic plot. You can just click run. But if you want to change the title or add a new title, you can just type main equal to apostrophe double apostrophe sign, and then just type the name of the title for the mosaic plot. Change the name of the y-axis and the x-axis. And if you click run, you can see here. And then just export it, save as image. You can change the height, etc. You can just save it. And I already save it here. So this is how the data for the mosaic plot for the data looks like. Moving on to the assumption test. So as usual, we have the normality test and the test for homogeneity of variance. But unfortunately, both tests cannot be performed as the variables, which is the gender, is a nominal data and the normal BMI status is an ordinal data. So both of them are not numeric, so we cannot perform the Shapiro, which is for normality test, and then the Levin test, which is for the test for homogeneity of variance. So if you just type, I just tried to show that we cannot perform that. So for the Shapiro test, as usual, we just type Shapiro test, open bracket, the name of the object, dollar sign, and then for this one we do not have something that we measured, so we just put the first variable and the second variable. Make sure it is separate because Shapiro is a test to it it is for the separated data, not for all of the data like the Levin test. So if you click run, also this one, if you click run, we cannot have any we do not have any result. The same as for the homogeneity test of variance. First thing we have to do as usual, just open the package for car. So we open library and then just search for the car here. This is the command, and then you just have to type the Levin test. Make sure it is the right spelling. This is the right spelling for Levin test, and then just the name, the dollar sign, the second variable, and then according to, and then the name, dollar sign, and the first variable. Just click run. As you can see, we do not have any result here also because we both data are not numeric, they are not continuous. And then once we know that we cannot perform the normality and the homogeneity of variance test, so we can conclude that the suitable statistical test is a non-parametric test. So statistical test that I chose is the chi-square contingency table because the variables are not continuous data. Gender is nominal data while normal BMI status is ordinal data. Thus, all the assumption tests cannot be performed, proving that the suitable statistical test is a non-parametric test. And then to further find the suitable statistical test in all the many non-parametric tests, we look at the types of the data, which is so the data that was the variables here in this experiment is the nominal and ordinal data. So that exclude only the chi-square test. So the chi-square test, it have the goodness of fit test and then the contingency table test. So we look at the absence of percentage data. If the goodness of fit, the chi-square goodness of fit test, it provided percentage data. So in this question, the percentage data is not included. So the suitable one would be the chi-square contingency table. So we continue to the statistical hypothesis. For the null hypothesis, it is the UMS female students have more normal BMI status frequency than the UMS male students, while the alternative hypothesis is the UMS female students, have less normal BMI status frequency than UMS male students. And then the criteria is set at alpha 0.05. We continue to the statistical test. So this statistical test, which is the chi-square contingency table, we make it in R. We test it in R. So in R, you can just type here the chi-square dot test, open bracket, and just state the table name. And if you click run, you can see the result here. So the result shows that the p-value is larger than 0.05 because the p-value is 0.7806, almost close to 1. And then in order to, if you want to examine other statistical output, you can save the test as output. So this is the command. You can just type the summary chi-test and then just read it as chi-test because you want to save the test as output, and then just click the table name. If you click run, you already saved the summary, and then you just want to type the name back, which is the summary chi-test. Then you can just type any $sign, and then you can choose which statistical output result that you want to see. So if you want to choose statistic, just click run. You can see the x squared. You can see any test, any statistical output that you want to see. Just choose. And then for the moving on, as we already know, the p-value, which is 0.7806, is larger than the critical value that we set earlier, which is 0.05. So the result shows that the p-value is larger than the critical value. Thus, we accept the null hypothesis. Null hypothesis earlier stated that the UMS female students have more normal BMI status frequency compared to the male UMS students. So to conclude, the statistical test chi-square contingency table result showed that the UMS female students have more normal BMI status frequency than the UMS male students, as the p-value is larger than the critical value, which is 0.05. That's all. Thank you.